everybody. Thank you for your patience while we figured out our technical issues, at least for the time being. So I'm Amanda Mejia, and I'm at Indiana University in the Department of Statistics. Thank you so much to Wooter for organizing this course.
Since we're recording,
thank you.
Have to use the mic.
Thank you to Wooter very much for organizing this course, which is on a topic near and dear to my heart, which is spatial modeling. So today I'll share with you work that me and my group have done on developing spatial Bayesian models for task fMRI activation. I will put the caveat that I got here today, got to Australia today, so I am a little jet lagged. I'm going to be at some point severely jet lagged today, but for now I'm feeling good, so hopefully this will go off smoothly. So anyway, thank you guys all for coming and learning about Bayesian modeling. All right, so my goal is to convince you that it should not be scary. All right, so first I'll give some introduction to Bayesian statistics, since it's a topic that I'm sure you've all heard of, but maybe have limited familiarity with. And then I'll tell you about the spatial model that we have developed for task fMRI analysis. So a spatial Bayesian version of the general linear model and its advantages and how it works. And then at the end, I will do a demo of the Bayes fMRI, our package that we've developed. This is a package that we've developed many years ago, actually, at this point. So it's well developed. It's pretty, well tested and stable. It's available on CRAN as well as GitHub. So we have a published demo, actually, and so I'll just really mostly point you towards that and how you can go through that demo to learn more about the package and how to use it. Okay, so first, Bayesian statistics. Okay, so if you have ever taken a stats class, you pretty much are going to always learn first about frequentist approaches. And you may not even learn that they're called frequentist approaches because frequentist techniques are really the status quo or the kind of default approach to statistical analysis. So with frequentist methods, the idea is that we use only the observed data to estimate the parameters, and this is typically done via maximum likelihood. So an advantage of frequentist methods is that they are fast and easy to compute. So think about something like the sample mean, which is, it couldn't be easier, right? Couldn't be more straightforward. The downside of these frequentist methods, of just using the data and not using any other information, is that any noise of the data is going to be reflected in the estimates. And there's not much we can do about that besides collecting more data, right? That's always the answer, is just increase your sample size. But we all know in fMRI that's a little easier said than done, especially in large data sets, when we have limited scan duration per participant. Okay, so the alternative that I'll tell you about today is Bayesian statistics. So in Bayesian methods, we take into account our beliefs about what we're trying to estimate. So typically we have some beliefs, right, about the things we want to estimate. You can think, for example, of a variance. A variance should be positive, right? Doesn't even feel like a belief because it's so factual, but that is a belief. And if we don't encode that belief in frequentist methods, we can actually get variance estimates that are negative if we have if we're trying to decompose the variance into different components. So something as simple as putting a prior that enforces a positivity constraint is a form of using our prior beliefs. And so we do this through a prior distribution, and then estimation is done by maximizing what's called the posterior distribution, which is a combination of the data and the prior. So the posterior reflects our updated beliefs after we've looked at the data, whereas the prior reflects our beliefs before we've looked at the data. And Bayesian statistics, Bayesian methods have been proven theoretically to result in better estimates, meaning they're closer on average to the true value of the parameter. The downside is that estimation can be more difficult, it can be potentially slower compared with frequentist methods. And I would argue that there's been a lot of improvements in Bayesian computation over the past couple decades, and if we leverage some of those improved approximate methods, we can get around the slowness and really come up with Bayesian techniques that are highly practical. Okay, so what are some prior beliefs we might have about task activation? So one example of a prior belief is that the pattern should be pretty similar across subjects. If I give you a motor task and ask you to move your finger, we basically know what area of the brain is going to activate at this point, right? It's going to be part of the motor cortex associated with the hand. And that's going to be similar across subjects. And so we could encode this type of belief in a prior that reflects the variability that we expect to see in the population. And we could build hierarchical Bayesian models to use that type of prior. Another example of prior beliefs that we may have about task activation is that the pattern should be similar for locations that are nearby to each other, for proximal locations. And this could mean locations that are close in Euclidean space. It can mean locations that are close along the cortical surface. It could mean locations that belong to the same parcel, right, based on some group parcellation. It could mean locations that are structurally connected. So we can define proximal in different ways. But this is a belief that we would probably, most of us would probably say this is a reasonable belief that we could encode through a prior. And so this is actually the type of prior I'll be talking about today, which is known as a spatial prior. So we're going to have a multivariate prior across different locations with the covariance representing the dependence that we believe should exist among neighbors, however we define neighbors. And spatial Bayesian models are the type of model that use this kind of prior. Okay, so just to give you some basic terminology. So let's let y be the observed data, and mu is some parameter that we want to estimate, or some variable that we want to estimate in the model. So we have three quantities. We have the likelihood, the prior, and the posterior. So the likelihood is actually what you are pretty much working with in frequentist statistics, even though you may not even learn about it, with that name. Typically, most estimation methods with frequentist techniques are based on the likelihood. So the likelihood represents the probability of the observed data given a particular value of the parameter. And when we do maximum likelihood, we want to choose the value of the parameter that maximizes the probability of the observed data. So basically, the choice of the parameter that's most consistent with what we observed in the data. Okay, so in Bayesian statistics, we have these two other things. We have the prior, which represents our prior beliefs about mu. So it's just the distribution of mu without any additional information. And then we have the posterior, which is the distribution of mu given the observed data. So that represents our updated beliefs about the parameter after we've observed the data y. So there's a mathematical relationship based on Bayes' rule between the posterior and the likelihood and the prior. So the likelihood, we know how to compute that because we've been doing frequentist statistics for a million years. The prior, that's something we've specified. So if we want to get the posterior, all we need to do is use Bayes' rule. And so the posterior can be written as the product of the likelihood times the prior divided by what's called the marginal likelihood. But if you think about it, if we only care about maximizing the posterior, like finding the parameter value that maximizes the posterior, we don't really care about the marginal likelihood because the marginal likelihood does not involve the parameter mu. It's not a function of mu, so it's a constant in mu. So you often will see it written this way. The posterior is proportional in the parameter value to the likelihood times the prior. So if all we're doing is coming up with a maximizer or the maximum a posteriori estimate, we can ignore the marginal likelihood. Another time we could ignore the marginal likelihood is when we have what's called a conjugate prior, which I'm not going to cover today because it's a bit out of scope. But if we have a conjugate prior, then we can ignore the marginal likelihood and just work with the likelihood and the prior. All right, so that's often a lot easier. Okay, so just to illustrate this, imagine that we have a Gaussian likelihood, we have a Gaussian prior, and actually that's a conjugate situation. So we get a Gaussian posterior as well. If you know anything about conjugacy, this is an example where I put a Gaussian prior on mu. We have a Gaussian likelihood, and the posterior turns out to be Gaussian also. So we have our likelihood, which is centered around say 55.8 or so. So that would be our MLE, is the value of mu that maximizes the likelihood. The likelihood actually looks like a probability distribution in mu, but it's actually not. So it's a totally different quantity, but it looks a lot like a probability distribution. But it won't have the properties like integrating to 1 that you would have for a probability distribution. Okay, whereas the prior and the posterior actually are probability distributions. So I've rescaled the likelihood so it can be plotted on the same scale here. All right, so let's say our prior says, well, I really believe that the value of this parameter should be between 55 and 65. So I'm going to put a prior distribution on that parameter that basically constrains the values between 55 and 65. Now the posterior then is going to lie somewhere in the middle of the likelihood and the prior. So here you can see the posterior is almost halfway between the likelihood and the prior. In practice, typically the posterior is a lot closer to the likelihood. So I'm drawing an extreme case based on very little data and a very informative prior. But in practice, the posterior tends to be much more similar to the likelihood than to the prior. So I've just drawn it this way for illustration. Okay, so this idea that the posterior mean or the posterior maximizer, the MAP, is between the likelihood, the MLE, and the prior mean is called shrinkage. So this is the concept of Bayesian shrinkage you may have heard of, is that the MLE is being shrunk towards the prior mean. So it's the MAP is somewhere between the MLE and the prior mean. Okay, so here we're talking about spatial Bayesian models. So what do I mean when I talk about a spatial prior? So I'm going to try to illustrate this in a very simple example. So I have a latent spatial map, and this is a continuous map, but I observe data at a set of discrete locations. So here I'm drawing 6 different locations on the brain. But in practice, of course, we'd have 10,000 or 100,000 locations. But just so we can kind of conceptualize it, I've drawn 6 locations. So that image can be represented as a vector of 6 values. So this is an image of task activation that I want to estimate. So I'm drawing it as a vector. So I have beta 1, beta 2, beta 3, beta 4, beta 5, beta 6, all organized as a vector. And so now we need to think about this as a random vector. So, okay, so if you've not seen random vectors, I'm going to give you a little bit of random vectors 101. So a random vector has an expected value. So the expected value of beta is equal to the means of those 6 individual random variables. So each of those betas is a random variable, right? So I have an expected value of each of those random variables. And the covariance matrix of beta is a 6 by 6 matrix with the variance of beta of the beta 1 to the beta 6 along the diagonal and the covariance on the off diagonals. I guess I can point, yeah. So we have the covariances. Okay, so we like to organize things in random vectors, especially when there is dependence among the variables. So if everything is independent, then I don't really need random vectors. I can just kind of product my individual random variables. But as soon as there's covariance, it becomes really convenient to organize my variables into vectors. Okay, so in the spatial Bayesian models, I'm going to be using a lot of random vectors. So spatial prior is simply a multivariate distribution on this random vector beta that encodes the dependence between locations. The prior, what I believe about the dependence between locations. So I've just drawn kind of a generic distribution here. This could be, there's many choices for the actual distribution, but I've drawn it kind of in a sense that it's parameterized by its mean and its covariance. So this covariance is the key because this covariance tells me how similar do I believe neighboring locations should be. You may be thinking, how do you choose the values, right? So actually in practice, in our models, the model will estimate the values of those dependencies as well as the variance, okay? So we don't have to arbitrarily set these numbers. Okay, all right, so that was kind of Bayes 101, so hopefully now you feel a little bit more comfortable with Bayesian statistics, hopefully. And so now I will tell you about the spatial Bayesian version of the general linear model that we've developed and that's implemented in this package Bayes fMRI. Okay, so you all probably know the general linear model. In the general linear model, we estimate the amplitude and the activation of different tasks, right, during a task experiment. So what I'm going to refer to as the classical GLM is a massive univariate approach. This is the standard approach to analyzing task fMRI data. Of course, there's many variants of the classical GLM, but fundamentally what we're doing is a massive univariate modeling where we're fitting a separate linear model at every location. So the Spatial Bayesian GLM, which as you can see I'm illustrating here that it, oh, where's my pointer? I cannot see any dots. Anyway, you can see in the images I'm illustrating that we get much smoother estimates, which you can see in our papers that we do. But we're trying to estimate the same thing, right? So the goal is the same as the classical GLM. The difference is that instead of fitting 100,000 models or 10,000 models, whatever your spatial resolution is, we're fitting a single model to all the locations in the brain that accounts for the spatial dependence between the different locations via spatial priors. And when we do this, we get much greater accuracy and much greater power to detect activations, especially in individuals. All right, so first I'm gonna just write a classical GLM model so that you can get familiar with kind of the notation that I'll be using. All right, so we have our, see if my clicker doesn't work up. So we have our observed bold signal at location V. So I'm writing this model for a single location since the classical GLM is a massive univariate approach. So this is my observed signal. So this is a t/1 vector. So I'm writing this model in matrix vector form. So it's a single location, but it's already in vector form since I've drawn y as a vector of length t. Okay, and what I want to estimate is the amplitude of activation for each of a series of tasks at every location. So beta k is the activation due to task k or stimulus k. Okay, and then x here is the expected bold response. That's my design matrix. And I've made, just for simplicity of exposition, I'm excluding a lot of nuances here, right? There's no nuisance regressors. So there's a lot of assumptions that I'm making with this model. So there's no nuisance signals, there's no baseline field, there's no intercept, and there's no temporal autocorrelation or heteroscedasticity across time. And these are important caveats. The reason that I'm writing it this way is just for simplicity, but of course we need to satisfy all these assumptions. So we can satisfy these actually. We can pre-regress the nuisance signals from the data into the design matrix. We can center the data in the design matrix to eliminate the intercept, and we can do pre-whitening to satisfy the assumption of no temporal autocorrelation. So we do all those things in the package, but here I just kind of skip over those details so that we can just focus on the core task activation aspect of the model. Okay, so once we fit this model for all of our V locations, we string out all of our location activation estimates so we can make the image, right? This is our statistical parametric map. And then we will do hypothesis testing at every location. And because we're fitting this model at, say, 10 to 100,000 locations, we need to correct for multiple comparisons correction, which you can pick your favorite method, whether it's permutation testing or Bonferroni correction or FDR, right? But you have to do some kind of multiple comparisons correction. And so you get your map of activation. This clicker is a bit on the fritz. Okay, here we go. Okay, all right, so I'm going to show you just a very simple toy example of using a spatial model in this context. So you can get hopefully some intuition of how the machinery actually works. Okay, so let's consider a single task, and it's just going to be a constant task. So it's essentially resting state is what we're actually doing. So the design matrix is just all ones. All right, so the likelihood is given by the same formula I showed you earlier for the classical GLM. So the likelihood is really just the model for the data without any priors. Okay, now I'm going to organize it into one big formula. So I'm going to take my multiple locations, V, and I'm going to string all that data into one huge vector, Y. And then I'm also going to organize my design matrix into a big sparse matrix X. And then beta is so I have a single beta. So beta is a V/1 vector. So now I'll put a prior on beta, which is in this case just going to be a multivariate normal prior. And I'm writing, I'm going to let the mean be 0. And the covariance is going to be Q inverse. So Q will be a sparse precision matrix, a sparse inverse covariance matrix. So that's getting a little bit ahead. but I'll explain shortly. All right, so Q represents our beliefs about the spatial dependence, the direct spatial dependence, among the task activation amplitudes in the beta vector. So this is that multivariate prior that I mentioned earlier, that multivariate distribution on beta that I mentioned earlier, where the mean is not really doing anything. There's a zero mean. It's going to do a little tiny bit of shrinkage towards zero, but the main feature of this prior is the covariance between locations. All right, so let's say I have 6 locations in the brain, not my same 6 locations I showed you earlier, and I can draw edges between them to represent the neighborhood structure. Now, of course, in real life, again, I'm going to have thousands of these locations, but what we actually have with cortical surface data is a mesh, right? And that mesh actually, so that's how the data is stored. That mesh actually gives us a neighborhood structure because the mesh consists of triangles that connect different vertices. So that's essentially what I've drawn here is a mesh. So that mesh can be written as an adjacency matrix. So that's a 6 by 6 matrix with zeros where there's no connection and 1 where there's a direct connection between 2 locations. So, and also 1 to the diagonal. So you can see like locations 1 and 2, this pointer doesn't work anymore, but locations 1 and 2 have an edge between them. So there's a 1 in that cell of the adjacency matrix. So the precision matrix is going to have positive value or non-zero values corresponding to the cells where there are a neighborhood structure. And what it's telling us is that we believe a priori there's direct dependence only between edges that are connected via the mesh that share a triangle. So this is an example of a spatial prior. We could build spatial priors in different ways, but this is an example of the type of spatial prior we can build based on the mesh structure of cortical surface fMRI data. Okay, so continuing this example, again, X here is just a column of ones. So the frequentist estimate, our standard ordinary least squares estimate, so it's actually equivalent to ordinary least squares. Ordinary least squares is equal to the MLE if we have normal residuals. If you've taken like linear models class, that might ring a bell. So our frequentist estimate of beta is actually just going to be the average bold signal at every location. And that's only because here our design is just a column of ones. So our estimate, our best estimate of the overall activation is just going to be the average signal at every location. So this is kind of a silly example. You wouldn't do this in practice, but just so you can see how the math kind of works out. Okay, so if we put that Bayesian prior on beta, the Bayesian estimate, the MAP that we would get, can be shown to have this form. So it's the exact same thing, except for now we have the plus Q. So that plus Q, depending on what Q looks like, is going to have an influence on the estimate of beta that we get. Okay, so let's go through a few examples. So what if Q is almost 0, just almost a matrix of zeros? So if we were to invert that, we'd get the covariance matrix. So remember, Q is the inverse covariance. So if we invert that, we get a matrix that's almost infinity everywhere, just really large values. What that means is that we have the prior variance is very large. So it's a very uninformative prior. And so then if Q is almost 0, then it will basically disappear from that equation, and the MAP will have the same form as the MLE. So if our prior is very what we say uninformative, very large prior variance, it's not going to have much of an influence at all. So the MAP, the Bayesian estimator, will be almost the same as the MLE. So what if instead Q is a diagonal matrix? So that's not a spatial prior, right? We've said a spatial prior encodes dependence. If Q is diagonal, it means there's no prior dependence among locations. So if Q is just a diagonal matrix, then that does not put any dependence a priori among the locations. It just puts a prior variance of 1. So it's going to do a little bit of shrinkage towards the prior mean. So the formula that we can come up with for the MAP has this form. And this, what I've circled, is what we would often refer to as the shrinkage parameter, lambda, or it's 1 minus the shrinkage parameter. And so that lambda is going to be a number between 0 and 1. And so we're going to have a little bit of shrinkage of that MLE towards 0, which is the prior mean. So as an example, if we have 100 time points, then lambda would be 0.99 if the variance in the data is also 1. So you can see it's just a tiny bit of shrinkage towards 0. Okay, so what if instead Q actually has a form that's consistent with its idea of a spatial prior? This is an example of a Q matrix that we could come up with that if we invert it, looks like has positive dependence between neighboring locations, actually. And then there's some indirect dependence between more distal locations if we do the inversion. So in that case, we can still come up with a formula that looks like the MAP is being related to the MLE, but instead of having a univariate relationship, it's a multivariate relationship. So there's a matrix lambda that's being pre-multiplied by the MLE. And so you can see what that lambda matrix would look like if we had t equal to 100 time points, and the residual variance was 1, then lambda, if Q is equal to that matrix, then lambda would look like this. So you can see there's some shrinkage happening along the diagonal. So there's 0.95, it's shrinking a little bit towards 0, but also there's some mixing of signals among proximal locations. So those off diagonals are going to cause some mixing of the signals. So it's actually doing a bit of smoothing, essentially, is what it's doing. Okay, so for example, the MAP at location 1 is equal to 0.95 times the MLE at location 1 plus some contribution from locations 2 and 4. And locations 2 and 4, if you look at the mesh, are connected, directly connected to location 1. Okay, so I'm trying to make this as high level, as simple as possible, but also I wanted to show you a little bit of how the actual machinery of a spatial model works. All right, so I'm going to not do any more, I don't think we'll have any more formulas in math, too much more math throughout. But I wanted to give you a little bit of an intuition for how these spatial priors actually work to encode that dependence. So there's essentially doing smoothing. So the prior itself is actually smoothing the estimates that we would get without a spatial prior. All right, so Spatial Bayesian GLM is basically, we have to do two things compared with the classical GLM. So first we have to organize the model into a single model instead of having V different models. So we just put everything together into one big matrix vector model. And then we are going to, so we have all of our ingredients, we have our bold signal, we have our design matrix, and we have our activation amplitudes. But this is actually the exact same model as the classical GLM I showed you before. It's just written as a single model instead of written as a bunch of different models. But there's no, if we were to estimate the beta vector, we would get the same thing. We haven't changed anything about the actual estimation procedure. So to get a spatial model, we have to put a spatial prior. So we're going to put a separate spatial prior on every task in the experiment, every task in the model. And that's going to be a multivariate normal prior with a specific form for the precision or the inverse covariance. Okay, so we need a spatial prior that can work on the cortical surface. So I haven't talked about this, but I think there's very good reasons to build spatial priors on the cortical surface rather than on the brain volume as a whole, because we have this. If we build spatial priors on the brain volume as a whole, we have the same problems as with spatial smoothing. We're blurring across tissue boundaries, right? We're blurring across areas of the cortex that are distal from each other. Whereas if we build a spatial prior on the surface, we'll get a smoothing effect along the surface. Okay, so we want a spatial prior that can be applied to triangular mesh data. It must have a sparse inverse covariance, otherwise the computations will be impossible. And also we'd like it to be multivariate normal, because that will make our lives easier. And so a type of prior, and the only type of prior to my knowledge that satisfies all of these boxes are termed SPDE priors. So these have been developed over the past about 15 years. Okay, so again, try not to go make it scary at all, but I do want to show you a little bit kind of under the hood. Okay, so we have this Q matrix. This is our inverse covariance. And this inverse covariance is defined by some matrices F and G, which are known. We We don't have to come up with those. They're determined based on the mesh structure. So they're fixed. They don't have to be estimated or anything. And two parameters, tau and kappa. So tau is a parameter that controls the variance or the scale of the latent field. So how large are the activations? Are we talking about percent signal change, or are we talking about some other scale? So we have a parameter that can determine what the scale of the field. And then kappa determines the amount of spatial correlation. So how much kind of smoothing effect will we get? Okay, I also want to show you that we can apply these models now to subcortical structures as well. So we're kind of in the spirit of gray ordinance, that we want to analyze all the gray matter of the brain, but we want to do it in a way that respects the cortical anatomy. So if we just focus on the cortical surface, of course we're ignoring everything that's going on under the cortex. So we don't want to do that. So what we'll try to do now is to extend these models to subcortical structures, and that is now available in the later versions of the Bayes fMRI package. So just to give you a sense of how we do that, if we have this lattice kind of volumetric structure, every voxel is going to be considered neighbors with the voxels immediately up and to the left and behind. So the 6 voxels that are immediately touching that voxel. And then the SPD prior will also assume direct dependence with the second degree neighbors. So we're going to have dependence with this type of neighborhood structure if we were in 2D. But of course, in 3 dimensions, we have a 3-dimensional version of this. Okay, so this is the type of spatial prior that we would have in a volumetric setting. So how is it different than just applying spatial modeling to the volume? So what we're going to do is to have dependence, assume a priori dependence within, say, the right thalamus, but then we're going to assume no dependence a priori between different structures, between, like, say, the right thalamus, the left thalamus, the brainstem, the cerebellum, the putamen, etc. So by having a prior that has this block diagonal structure in the prior covariance, or the prior inverse covariance, we're assuming no direct dependence between structures. And what that's going to do is kind of like a partial constrained smoothing. So the prior will smooth within each structure, but not across structures. All right, so that's kind of how the most basic overview of how we extend these models to the subcortex. So that's, again, available in the package now. Okay, how do we estimate areas of activation? So this is one of the most important contributions of these spatial Bayesian models. So we use the joint posterior distribution of each of these latent fields to identify areas of significant activation. So we completely avoid multiple comparisons unless you want to control for multiple comparisons across tasks or something, but no one really does that, right? So we don't do any multiple comparisons across locations. Unlike if we were to use the marginal posterior, which is something that was done in earlier spatial Bayesian models for volumetric analysis. So we have a dramatic gain in power over massive univariate modeling, and also a gain in power over the marginal, the use of the marginal posterior, because doing the marginal posterior requires correcting for multiple comparisons. So since we do not have to correct for multiple comparisons, and because we're leveraging spatial dependencies, we see a massive gain in power. Because we have such high power, we can also specify a scientifically meaningful minimum effect size to avoid just detecting very small activations. And in a Bayesian sense, the procedure that we develop controls the family-wise error rate, since the posterior probability of a single false positive is controlled at less than or equal to alpha. Okay, so I'm going to not go into any details here. The one thing I want to say is that you do have to specify 2 things, the significance level and the minimum effect size. So significance level is like, say, 0.05, 0.01, whatever your favorite alpha is. The minimum effect size is it's not a threshold, it's the basis for the hypothesis test, essentially. So typically when we do a hypothesis test, we're testing against 0, but that's not the only choice, right? We could test against a larger value. Let's say I want to identify significant activations over 1% signal change. So that's what gamma does. So we have to specify that. So often we'll choose like 1% signal change or 2% signal change or 0.5%, just kind of depending on what we're interested in that study or what we think the level of activations will be with that particular task. So we need to specify both of those values. Okay. All right, so just some snapshot of some results from a paper that we published in 2022 validating this approach. So this is 3 different individuals in the HCP, and this is from the motor task, which is actually a pretty highly overlapping task. But what we see is clear differences in the form of activations across these 3 individuals. This is the tongue task. You can see this kind of unique spatial topography of these 3 individuals. And this is from the overlap across 2 visits. So you can see it's highly replicable across the 2 visits. And in terms of the power, we're showing activations over 0, 0.5, and 1% signal change in the yellow, red, and purple. And at 0, you can see the Bayesian GLM will give a lot of activations, even in areas where it's just a subtle activation. And this is 2 runs. So this is a single visit, 2 runs, LR and RL. So this is not like an enormous amount of data, right? These are 2 like 5-minute runs. So we're getting high power even for a very modest amount of scanning at the individual level. And then we can also kind of focus on those higher activations. So we can see the 0.5% activation kind of starts to show the core area of activation at the individual level. So there's activations in red. And these are much larger areas that we would get if we did a classical GLM, even if we did smoothing. All right, so, and then you can check out this paper. This is named here, but also on my website. Okay. All right. We can also do group averages. I'm going to skip this for time, but we can do group averages in a principled way. And we also get much higher power compared with the classical GLM. This is also implemented in the package. All right, just on the topic of group averages, I want to say that because we have high power at the individual level, we often find it more useful to look at proportions of the number of subjects that activate in different areas compared with looking at group averages. So here's an example from, I think is this like a gambling task? It's one of the tasks that doesn't have a lot of overlap across subjects. And what you can see is that there's just a lot of idiosyncrasies across the 3 subjects that I'm showing in terms of where exactly the activation occurs. And if I do a group average, a lot of the individual activations are going to be attenuated because of the lack of overlap. And so my group average map is not, it doesn't show much over 0.5%, whereas the individual maps actually do show activation over 0.5%. And so one thing that we find useful in this approach, because we have high power at the individual level to detect significant activations, if we average those binary maps, we can get a proportion of subjects active at a certain level of signal change. So this is a map of the proportion of subjects that are active at a level of 0.5% signal change or higher. So anyway, we find this particularly helpful for tasks where there's not a ton of overlap in terms of the topography. All right, so with that, I think we only have a few more minutes, so I can point you towards our demo and kind of maybe if we have a few minutes, show you a little preview of the demo. So I want to point you towards the relevant locations. So the package itself is available on both GitHub and CRAN. I recommend installing it from CRAN just with install.packages. We're in R, by the way, if you haven't figured that out yet. We're in R world. We're in R world. And so everything is in R for this package. So you can download it from CRAN with install.packages, or you can get it from GitHub. One of the benefits of doing it, so I recommend using CRAN for just installing. But if you go to GitHub, you'll find the vignette, and you can actually find the vignette data and go through, so the vignette's a demo. So in our language, a vignette just means a demo. And so the data for the demo is available on the GitHub version of the package. I don't think it's on the CRAN version. And so the demo itself can be downloaded. If you just clone the GitHub repo, you'll have access to the actual vignette. But if you just want to preview the vignette, there's a link on my software page for my lab website. So that's just like an HTML preview of the demo. So you can see it fully rendered, but that won't get you to the R Markdown and all the data and everything. For that, you'll need to go to the GitHub page for the package. Okay, so we have a few minutes to look at the demo? Woodrow, you tell me.
Sure.
Okay, how much time do we have? And I can send out these links on the Slack channel as well. Oh, and also the slides. The slides are available on the page that Woodrow sent out earlier. Okay, got it. Great. Thank you. Okay, can everybody hear me? I guess you can, yes. Okay. All right, so I'm going to kind of point you towards the right places to learn more. So first of all, I would recommend going to statminelab.com/software. If you see the Bayes fMRI sticker, you can click on the vignette, and that will open up this HTML file. And so this is going to show this is kind of like a Jupyter notebook if you're more familiar with Python, but it's called R Markdown in the R world. And so this is going to walk you through the package and its main function, which is Bayes GLM, as well as downstream functions like activations that you can use to implement the activations technique that I talked about. And so it'll talk about installation. We have a number of dependencies, including the Connectome Workbench, the Sifty Tools package, and the INLA package, the R INLA package. This R INLA package works splendidly on Macs, but there is a bit of nuance for Linux systems. So if you're a Linux user, just be aware that you may have to do a bit more troubleshooting to make sure you actually have that package properly installed. Okay, so it'll walk you through the basics of setting up the model. We're going to use the Sifty Tools package, which allows us to read in Sifty data. If you don't have Sifty data, but instead you have, let's say, Gifty data, you can also use this package to set up a Sifty object in R and pass that into the function. And so here you can see that we have left cortex data, right cortex data, as well as subcortical data that we've read in. Okay, so the setting up the design matrix. Okay, here we have two tasks. This is a motion task from the HCP. And so now we're going to call the main function, which is Bayes GLM. And this takes, in this example, this is about 3 minutes it'll take. So you can see here how long it prints out how long it took. So it's not a very, it's a pretty fast function for certain models. It depends on how much data we're trying to analyze. And then we also have some visualization tools built in. So you can see the spatial, the estimate for the fear condition. This is the classical estimate for the fear condition, which is much noisier. And then we have the subcortical. So you can see the fear condition and the areas we've analyzed, which were the amygdala and the hippocampus. You can see here we specified we wanted to analyze the amygdala and hippocampus. So you can see that we get much cleaner looking activations in those two areas versus the classical GLM. And then for identifying areas of activations, we call the activations function. So I'll show you those. So this is our cortical activations based on the spatial Bayesian GLM from the fear condition, and then the classical using Bonferroni correction, but we only have 10,000 locations, so Bonferroni is actually not terribly conservative compared with, say, permutation testing in this context. So you can see it's a lot less powerful. And then even FDR is identifying a lot less than the spatial model. Now, to be fair, we haven't smoothed this data, but even with smoothing, we typically see greater power, even compared with FDR, with a spatial Bayesian model. Okay, here we have our subcortical activations. And then we can also do second level modeling with Bayes GLM2, so it'll walk you through that. We can have our group average for fear, our group average for neutral, and our subcortical activations, or subcortical estimates, and then our areas of activation for fear, as well as the subcortical activations for fear. And then we can also do contrasts as well through Bayes GLM2. So this will walk you through all of that. So I think, and finally, a prevalence map. So there's a prevalence function that allows us to construct those probability maps of what percentage of subjects show significant activation across the cortex or in the subcortex. We can also do prevalence map testing using basically a type of statistical test that's appropriate for binomial data. So we can find areas of where, so let's say at least 50% of people tend to activate. So this is a different approach towards group level analysis than typical group averages. Okay, so that's about it. I think for the sake of time, I'll stop there. But I hope that I provided some good places for you guys to start if you want to start using this. Just to show you also the GitHub repo for this package. So if you want to download this or clone this, you'll have access to the vignette itself. So if you go into the vignettes folder, you see the RMD file here is what you'll need to open to actually work through the vignette yourself and make sure that you have everything set up properly to run the analysis. All right, with that, thank you so much.